So folks, I think the key insight that I have for this section about converting between polar and rectangular coordinate systems is that if I start off with the Cartesian coordinate system, the xy rectangular system, here's x, here's y, and what we'd like to do is draw a connection between that two-dimensional coordinate system and the polar coordinate system where we were working with points in each of these. So one way to think about this is, let's say I had this point right here of r comma theta sitting in my polar coordinate system. What I'd like to do is think about superimposing this coordinate system on top of the other one. And so rather than trying to get to that point by moving out a certain radius and then going up a certain angle to arrive at that point, I'm going to use the rectangular coordinate system. And so one way to think about that is we'll move out this far along the x-axis and then up this far in the y-axis direction, and that will get us at that same point. And so it's that connection there that we just drew that enables us to convert back and forth between the two coordinate systems. So to go from polar to rectangular, we could go ahead and say that, if we have our r and our theta, that x is equal to r times the cosine of theta, and that y is equal to r times the sine of theta. And so what that says is we could take an ordered pair r comma theta, and we could find an x coordinate about it by simply taking and finding the length of this side right here, given that we know the radius, which is the hypotenuse of this right triangle, and then the angle theta, we can find that x coordinate. And likewise, we can do the same thing with the y coordinate here using that. So alternatively, if we want to think about going from the rectangular system to polar, well, here we could make use of our identities. And for instance, we would notice that if I were to square both sides of, if I were to add these two equations together, we'd have on the one hand side, we'd have x plus y. I'm sorry, let's first square each of these equations and then add them together. So if I were to square the first equation, I'd have x squared is equal to r squared cosine squared theta. And if we then took the second one, we'd have that when we square it, we'd have y squared is equal to r squared sine squared theta. And then if we sum these two together, we would have that x squared plus y squared then was equal to the sum of r squared cos squared theta plus r squared sine squared theta. And then using the Pythagorean identity, we get x squared plus y squared is equal to r squared. Okay. Finally, if I were to take these two equations and divide the first equation by the other, I would end up with y over x. I'm dividing the second equation by the first one, and on the right hand side I would have r sine theta over r cos theta, but that gives us the second conversion that the ratio of y over x is equal to the tangent of theta. So if we know our x and y, we can solve for r this way, and if we know our x and y, we can solve for theta by using the inverse tangent function. So folks, in this next example, what we want to do is we want to take a region R and just sketch it. So I want to make sure we're getting comfortable with this polar coordinate system. So let's give it a shot here. So I'm not going to be very careful with drawing out concentric rings and whatnot, but here we've got our pole in our polar axis, and we're saying our radius is ranging between 1 and 4. So let's go ahead, and here's a circle of radius 1, and let's just say here's that's pretty ugly. So here's a circle of radius 4. That's somehow less ugly. And then we're going to give ourselves the angles between minus pi over 4 and 2 pi over 3. So let's see here. Here's the angle minus pi over 4. There's where theta equals minus pi over 4. And I could extend that through if I wanted to, but I'm just going to, because I know what this region is eventually going to look like, we'll just stop there. And then the angle 2 pi over 3. Which we'll go ahead and draw, 2 pi over 3, let's be a little careful there, 2 pi over 3, which would be out here. There's the angle theta equals 2 pi over 3. Let me scoot us down just a hair. I guess we don't need that. Okay, and so then what's our region here? Our shaded region should be this region right here that I've shaded, that is our region R in this case. Okay. By the way, the two concentric circles with the hole cut out of the middle, sometimes you might call that a washer, maybe a flat washer or something like that. Another name for it is to call it an annulus. Okay, so I'd like you to try, that was number 4, I'd like you to try number 5 on your own, and you can click the link for help there, and then we'll move on. Let's go ahead and describe this region now in terms of polar coordinates. So we've got x squared plus y squared. Well, that's actually, I mean, we could do the substitution, right? I mean, we could first say, well, let's let x equal r cos theta, let's let y equal r sine theta, and then start plugging those in to these two expressions here. But one thing that we see is that we've already got the substitution where x squared plus y squared, we know we can substitute with r squared. Okay. And for doing the second one, we could try to do some sort of trick with r sine theta. But I think what we'd have a better time doing is let's go ahead and sketch this region first in the rectangular coordinate system. And so this is again another one of those annuluses. So here we've got the circle with radius 1, but our region is bigger than that. And here we'd have a circle with radius what? Careful folks, the radius of the circle would be the square root of 3 for the outer one. And for the inner one, let's see, we want y greater than equals. So for the inner one, that would be the circle of radius 1 here. And we want the y coordinates to be greater than 0. So let's go ahead and finish shading out this region here. I'm shading it in red, I guess, in this case. So that's the region R. Oh, I think that's a thing in pop culture. Oh, well. So we've got that region R there that we've shaded. Now we want to describe that in polar coordinates. Okay. Well, we certainly see that r squared has to be between 1 and 3, or put another way, then our r values have to be between, well, let's go ahead and just do this for a positive radius. And so then our r values have to be between 1 and the square root of 3. If we had a negative radius, notice it doesn't change the region we're talking about, so we don't need to worry about that. Okay, and for when our y coordinates are greater than 0, what angles give me that? Well, it would be this angle right here, which is just the angle theta equals 0 along our polar axis, and then we could open it all the way up here, and that's to where theta equals pi. So I think we're ready to go ahead and describe this region in polar coordinates. We've got r is equal to the set of polar coordinates r comma theta, such that we said 1 must be less than or equal to r, must be less than or equal to the square root of 3, and we need to have theta between 0 and 2 pi, or excuse me, 0 and pi. So we've got 0 is less than or equal to theta, which is less than or equal to pi. Okay. So I'd like you to now try number 7 on your own, and there will be a link there for you to click to check your work.